So this is a really neat section. So far in your career in algebra, all you've been able to do is find zeros or find where it crosses the x-axis. Another way to say this is find roots of a polynomial that was either quadratic or linear. If it wasn't, then you needed to recognize how to factor it in order to find those zeros. So this section is going to give us all these tools to be able to find zeros or intercepts, x-intercepts, same thing, of polynomial functions. And so there's a lot of different theorems that will help us narrow down our search to find out what those zeros are. And so I just wanted to go quickly through the objectives just so you kind of get the names, but you should be able to use the remainder and factor theorems, which all of these I'm going to give to you in a second. Well, a little more than a second. Use the Descartes rule of signs to determine the number of positive and the number of negative real zeros of a polynomial function. All these page numbers are page numbers in your textbook that would bring you to these theorems. Use Rational Zero Theorem and list the potential rational zeros of a polynomial function. Find the real zeros of a polynomial function. Solve a polynomial equation. Use the theorem for bounds on zeros. And use the intermediate value theorem. So like I said, there's a lot in this section and a lot that you probably haven't seen before in your algebra class. So first thing that we want to look at is long division of polynomials. So we have this division algorithm, and the division algorithm states the following. So if f of x and g of x denote polynomial functions, and if g of x is a polynomial whose degree is greater than 0, then there is a unique polynomial function, q of x, and little r of x, for which, so dividing f of x by g of x, this is equal to q of x plus r of x over g of x. Or another way to state this is, and this is the way that we're going to be using it for this class, if we can divide f of x by g of x, this is equal to q of x times g of x plus r of x. So just terminology, what we're dividing into is called the dividend. What we get back after we divide is called the quotient. We were dividing by the divisor, and r of x is the remainder. So our goal in this section is to get remainders that are 0, because then we know it's a factor of our polynomial. Our divisor and our quotient are factors of our polynomial. So let me finish this off. So this division algorithm where r of x is either a 0 polynomial or a polynomial of degree less than that of g of x. So if our degree is the same or bigger for r of x, that means we haven't divided all the way through. We can continue to divide. Let me pull an example. So we have f of x and g of x. We're trying to find f of x divided by g of x. F of x is the polynomial negative 4x cubed plus 5x squared plus 8, and g of x is the polynomial x plus 3. So let's first look at this with long division. So long division of polynomial, our divisor, what we're dividing by, which is x plus 3, is going to go outside. And our dividend, what we're dividing into, is going to go underneath. So if you're missing any term with power, when you go descending order of powers, then you want to put a 0 in for that. So notice that our f of x function, there's no x term. I have a cube, a squared. I don't have the first power of x. And so in that case, we could rewrite f of x. So let's just do that right now. As negative 4x cubed plus 5x squared plus 0x plus 8. So this is just a placeholder, and this is helpful for us so that we're lining up like terms when we're doing this division. Okay, so think to yourself, what do I need to multiply this first term? That's the only one I'm worried about in my divisor to get this first term in my dividend, negative 4x cubed. So I know to get from an x to an x cubed, I need an x squared and I need a negative 4. So negative 4x squared times x is going to give me that first term in the dividend, negative 4x cubed. Okay, so negative 4x squared. So we're taking that value that we found and we're going to distribute it to each term in our divisor and put it below the dividend. So negative 4x squared times x is negative 4x cubed, which we wanted. And then we have negative 4x squared times positive 3. So that's going to give me a negative 12x squared. So recall when you're doing long division, once you multiply that, and you put it underneath the dividend, then you subtract that off. So we're going to subtract off this whole value. And so a negative 4x cubed, this is really now a plus 4x cubed. That's a 0x cubed, so I don't have to write anything. And then I have a 5x squared, distributing my negative here, plus a 12x squared. So that's going to give me a 17x squared. And then we're going to bring down our next term. So plus 0x. So we're going to do the process again, but this time we're looking for numbers that multiply to give us the 17x squared. So x times what is 17x squared? Well, that's 17x. So 17x times x, that's 17x squared. And 17x times 3, that's 51x. And so we're going to subtract this off, and that was positive. So if we subtract this whole thing off, 17x squared minus 17x squared cancels. And then we have the 0x minus 51x. So this is going to give me negative 51x and then plus an 8, bringing down my last term. So we're repeating that process again. We're looking at what multiplies to give us this first term down here after we subtracted negative 51x. What can we multiply negative x by to get negative 51x? Well, that would just be a negative 51. So distributing negative 51 times x, this is negative 51x, and negative 51 times 3. That's going to be a minus, let me see, 153. Again, we got to subtract off this value. So a negative 51x plus a 51x cancels. And an 8 plus a 153, that's going to give me a 161. So notice 161 is my remainder. The degree here is 0. It's less than the degree of my divisor, which is 1. And so I can write this as f of x, this polynomial, is equal to our divisor, which is x plus 3, times our quotient, which is minus 4x cubed, no, not minus 4x squared, not cubed, plus 17x minus 51 plus our remainder. And our remainder is 161. So plus 161. Really, again, in this section, we're trying to get to that remainder being 0. And so this would tell me that x plus 3 doesn't divide into f of x evenly because my remainder is not 0. If we have a factor, so if you have a factor in the form of x minus c, or actually, maybe I shouldn't say factor because we don't know if it's a factor. That's what we're trying to find. But if we have a divisor in the form, so if the divisor is in the form of x minus c, then you can use synthetic division. To divide. So normally we're checking to see if something x minus c is a factor of our polynomial. And so we're going to, instead of using the long division like I just did, we're going to be using synthetic division. So it's really that c value is the opposite sign that's in here. And then you're going to list right in here, the top horizontal. So list the coefficients. So remember the coefficients were the numbers that were in front of your variable. So list the coefficients in order from descending order of power. Of the dividend. So what we're dividing into. Just like we did for this example, and I'm going to show you this example again, but using synthetic division, showing we get the same thing. But if we have a term that has a missing power, we would need to put 0 in here, or it's not going to work. So replacing 0. For missing terms. And then the constant. So let's go back to that same example, and I'm going to show you how to use synthetic division with that long division that we just did, instead of using long division. And so we're dividing by x plus 3. So it's the opposite sign. So I'm going to use -3. We're going to write the coefficients. And our coefficient for f of x, that is -4. Let's leave a little bit of space in between each one. We have a 5 in front of the x squared. There's a 0 in front of the x, and then our constant 8. And then the horizontal line below. Okay, so now we are ready to use our synthetic division. First step you're going to bring down the first coefficient. So if I bring down that first coefficient of -4, and then we're going to multiply C and the coefficient on the bottom row. And then place it underneath the next coefficient. So if I multiply my -3 times this -4, that gives me +12. And now we're going to want to sum these. So 5 plus 12 that gives me 17. And now we're going to repeat the process. So I'm going to take my C value and my C value, which is -3, and multiply it by that last number on the bottom row. So -3 times 17, that's -51. And I'm going to put that number underneath the next number. Sum this up. So we have 0 plus -51. This is -51. Multiply by our C. So -3 times -51, that gives me 153. Sum this up. 8 plus 153 is 161. So the bottom row here, this is the numbers, our coefficients, in front of our variables for our quotient. We have to start 1 degree less than the quotient. I'm sorry, not the quotient, the dividend. What we have on that bottom row is our quotient. So our f of x value, that was a cube. And so 1 degree less than a cube is a square. And so our q of x value, our quotient, is equal to -4x squared, and then just go down in descending order of powers. So that's positive, so plus 17x minus 51. And the last number, this is always the remainder. So our r of x, and I guess they did a little r, is equal to 161. Let's just go back. That's exactly what we got with long division. So our quotient was up here, this -4x squared plus 17x minus 51. And our remainder was 161. And so this is a way that we can do this that is a lot faster. We don't have to deal with the variables in there. And it's a lot faster and a lot cleaner. And again, our goal is to try to find these values that are going to give us a remainder of 0. And that brings us to our first theorem. Let me blow this up a little bit. So our remainder theorem states the following. Suppose f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. Okay, let's look at what we just did and show that that's true. We just divided by x plus 3. And this is saying that my remainder would be the same thing as if I looked at f of 3. Let me just write down f of x again. So f of x was equal to negative 4x cubed plus 5x squared plus 8. And we were dividing by x plus 3. So I'm sorry, this shouldn't be, it should be negative 3 in here, not positive 3. Okay, so wherever we see an x, we're going to plug in negative 3. So I have negative 4 all times negative 3 quantity cubed plus 5 all times negative 3 squared plus 8. Order of operations, first do our exponent. So negative 3 cubed is negative 27. So I have negative 4 times negative 27 plus 5, negative 3 squared is positive 9 plus 8. Negative 4 times negative 27 is positive 108 plus 5 times 9, which is 45 plus 8. So that's going to be 153 plus 8, which is 161. So this remainder theorem gave us what we saw. Our remainder was when we did long division and we did synthetic division. So this is just a process of, again, helping us to find factors. We really want that remainder to be 0. This remainder theorem doesn't tell me anything like what the quotient is. It just tells me that if my factor, what I'm dividing by, or if what I'm dividing by is a factor or not. It's only a factor if my remainder is 0. Which brings us to another theorem. So we have the factor theorem. So suppose f is a polynomial function, then we say x minus c is a factor of f of x if and only if f of c equals 0. So our remainder that we get back is 0. Then what we were dividing by, x minus c, is a factor. So another way to state this, so the factor theorem actually consists of 2 separate statements. If f of c equals 0, then we know that x minus c is a factor of f of x. But we can also go the other direction. If x minus c is a factor of f of x, then we know then f of c must equal 0. We're going to use that in a minute. So our whole goal is to find zeros of those factors. We're going to use that in a minute, or we're going to find those in a minute and use this factor theorem to help us, or zero theorem. So here's another theorem that says the number of real zeros. So if you have a polynomial function cannot have more real zeros than its degree. And when we're counting our zeros, we count our multiplicity. So if you had like x minus 2 quantity squared, then 2, which sets x minus 2 equal to 0, would have a multiplicity of 2. And so multiplicity of 2, so x equals 2 and x equals 2 are zeros. We would count both of those. Okay, so here's the main theorem that we're going to be using. Your book actually gives a second, but this is the one I use first The other ones are just helpful to kind of narrow down our search. So this is a pretty cool theorem, and it's called the Rational Zero Theorem. Okay, so a couple of things. We can only use this if our coefficients are integer coefficients. So the next result, called the Rational Zero Theorem, provides information about the rational zeros of a polynomial with integer coefficients. So we're not going to have any imaginary numbers in there. We're not going to have any radicals. They have to be integers. So let f be the polynomial function of degree 1 or higher of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0, where a sub n doesn't equal 0 and a sub 0 doesn't equal 0, where the coefficient is an integer. Each coefficient is an integer. If p over q in lowest form is a rational zero of f, then p must be a factor of a sub 0 and q must be a factor of a sub n. Okay. So what we're doing, we're looking at p. P equals factors of the new P is factors of a sub 0. And Q, these are factors of our leading coefficient, a sub n. So what this is saying is, if I look at each factor of P of a sub 0 and put it over each factor of my a sub n value, if I have a rational zero, it has to be one of those. Unfortunately, what it doesn't tell me is if a radical is a 0, so a irrational number is a 0 or not. So if square root of 2 was a 0, this theorem won't help me. But it's going to help me narrow down my search and break down my factors into smaller and smaller factors. The other thing it doesn't tell me is if a complex number is a 0 or not. But we're going to use this a lot to help us break down our polynomials and find the zeros of those polynomials and factors of our polynomial. So let's start with the following example. So let's say f of x, this is equal to, let's start easier. So negative x cubed minus x squared plus x plus 1. And this wants us to find all the possible. So it doesn't tell us what they are, but these will be the possible rational zeros. Okay, so normally what I do is I look at factors of my constant. And so I will list those out. Well, my constant is 1. So the only thing that goes in there is 1 and negative 1. Those are the only numbers that go in there evenly. I put the plus or minus out here because each number we find, it could either be positive or negative. Q, which is negative 1, well, the only things that go into negative 1 evenly is 1 and negative 1. So if I look at all my results of what P divided by Q can be, well, I have a negative 1 over positive 1, which is negative 1. I have a 1 over positive 1, which is 1. And then anything else combination are going to give me what I already listed. So pretty darn cool. If this polynomial has a 0, that's rational, then negative 1 or 1 are going to be it. There's not going to be any other possibility. And so we've narrowed down our search a lot. And so we can use that zero theorem, or we can looking at our factors. So let's practice with our synthetic division, and let's look at if x minus 1 is a factor. Let me just give myself a little more room. So my question to myself is, x minus 1 a factor of f of x? And so I'm going to try by using synthetic division. And so I have 1 in this upper left-hand corner, and now I'm going to list my coefficients of f of x in order from descending order of powers. So we have -1, -1, 1, and 1. There are no missing terms, so I don't need to put a placeholder in there. Bring down our first number, -1, and then multiply it by our c value, which is 1. So 1 times -1 is -1. Sum this up. -1 plus -1 is -2. 1 times -2 is -2. Place it under the next number. 1 plus -2 is -1. And 1 times -1 is -1, which this gives us 0. So is it a factor? Yes. Our remainder equals 0. And so x equals 1 is a 0 of f of x. And we can say, like I just put up there, x minus 1 is a factor. So let's write what f of x is so far. So f of x, we can break it down, is equal to x minus 1 times our quotient. And our quotient, those are our coefficients. We're starting 1 degree less than what our f of x value was. And so that's a cubic, so we're going to have a square. So we have -1 times x squared, so -x squared, minus 2 times x minus 1. So from here, I have a quadratic equation. I can technically see if this is factorable. I don't have to go through this synthetic division again to see if it's factorable or not. Let's try pulling out a -1 and then see. So I'm pulling a negative out of this x squared. So now we'll have x squared plus 2x plus 1, all times x minus 1. So I notice that is factorable. So the two values that multiply to 1 and would add to a 2 is x plus 1. So I can write that as quantity squared, x plus 1 times x plus 1, all times x minus 1. So we were able to factor this. We had x equals 1 was a 0, but x plus 1 equals 0 when x is -1. So x equals -1 is also a 0, but that 0 has multiplicity 2. And so if I look at this, right, multiplicity 2, so there's 2 zeros there, plus 1 0 here, that's 3 zeros. And that last theorem, I think maybe it wasn't the last one, said one before the rational zero said that, look at our degree of our polynomial. There can be no more than that degree for the number of zeros. It's actually going to equal that degree, but we're going to have to count both real and complex numbers that are solutions. Okay, so the last example that we're going to do for today is use the rational zero theorem to find all the real zeros of each polynomial function. Use the zeros to factor f over the real numbers. And we're given f of x equals 3x cubed plus 6x squared minus 15x minus 30. So p is equal to factors of our constant. Which in our case is negative 30. So numbers that go evenly into 30. I really don't care about the negative because I have plus or minus here. So numbers that go evenly into 30, 1 goes in there, 2 goes in there, 3 goes in there, 4 does not, 5 goes in there, 6 goes in there, 10 goes in there, 15 goes in there, and 30 goes in there. So that's quite a bit of numbers, but still, I mean, it's narrowing it down out of an infinite number, right? And then Q, these are factors of my leading coefficient. So Q are factors of 3, so 1 and 3, plus or minus. So now I want to look at each combination of P divided by Q. And if it's already in there, if it's already in that set, I'm not going to rewrite it. So we have 1 divided by 1, which is 1. I have 1 divided by 3, which is 1/3. So I'm going to go to my next P value. 2 divided by my first Q value is 2, and 2 divided by 3 is 2/3. Now I'm going to go to 3, my next P value. P divided by 1, my first Q value is 3, and 3 divided by 3 is 1, but it's already listed. Go to the next P value. 5 divided by 1 is 5, and then 5 divided by 3 is 5/3. 6 divided by 1 is 6, and 6 divided by 3 is 2, but it's already listed. Go to 10. 10 divided by 1 is 10, and 10 divided by 3 is 10/3. 15 divided by 1 is 15, and 15 divided by 3 is 5, but that's already listed. Last number, 30 divided by 1 is 30, and 30 divided by 3 is 10, so that's already listed. And these could be plus or minus. So this is where we have these numbers. We want to break down this polynomial f of x, and we're hoping that when we try the synthetic division or the remainder zero theorem, that we get back 0 for our remainder. So let's just start doing it. I would probably not do my fractions right away. And then on Thursday, I'll give you some more tricks to narrow down those values from our rational zero theorem. And so our first coefficient of our dividend, f of x, is 3. We have 6, we have negative 15, and we have negative 30. So bring down our first number. 1 times 3 is 3. 6 plus 3 is 9. 1 times 9 is 9. 9 minus 15, so that's negative 6. 1 times negative 6 is negative 6. This does not give me a 0 here, so I'm going to move on. So let's try 2. So a lot of this is trying numbers just to see if we can find that remainder of 0. So bring down 3. 2 times 3 is 6. 6 plus 6 is 12. 2 times 12 is 24. Negative 15 plus 24 is positive 9. 2 times 9 is 18. But that's going to sum to negative 22. I'm sorry, not negative 22, negative 12. So that does not equal 0. So if I tried 3, so bringing down my 3, 3 times 3 is 9, 6 plus 9 is 15, 3 times 15 is 45, negative 15 plus 45 is 30, this is 90, this doesn't give me 0. So this is now where I know from my rule that you guys don't know, but I do, that there's no positive number bigger than 3 that would work. And so I would probably start testing my negative numbers. And so let's try negative 1. So rewrite our numbers down. So 3, 6, negative 15, and negative 30. So let's bring down our 3. 3 times negative 1 is negative 3. 6 plus negative 3 is 3. Negative 1 times 3 is negative 3. Negative 15 plus negative 3 is negative 18. Negative 18 times negative 1 is 18. And that's going to give me negative 12. Doesn't work. So let's try another one. Okay, so now let's try negative 2. And I wrote negative 3. So negative 2. Now that's 3, 6, negative 15, and negative 30. Bring down our first number, 3. Negative 2 times 3 is negative 6. Negative 6 plus 6 is 0. Negative 2 times 0 is 0. Negative 15 plus 0 is negative 15. Negative 2 times negative 15 is 30, and this is 0. So that tells me x equals negative 2 is a 0. But it also tells me that x minus 2, x minus 2, x plus 2 is a factor. Of f of x. And we even know what this polynomial is. So far we have f of x is equal to our factor, which we just divided by x plus 2, times this bottom row. This bottom row, I started with a cubic, so this is quadratic. This is going to be 3x squared plus 0x, which I don't have to write, minus 15. I see I can factor this. Let's pull out a 3. So if we pull out a 3, we get x squared minus 5. And basically, that's a difference of squares. I can think of square root of 5. If I square that is 5. So I can think of this as x minus square root of 5, x plus square root of 5. So we broke this down into linear factors, plus we found all the zeros of f of x, which are negative 2 and negative root 5 and positive root 5. Notice root 5 and negative root 5 are irrational numbers, so they would not be in our list of p over q. But our rational number, our integer negative 2, was in that list. So we would never get a number that was rational that was not in this list. So we'll get some more practice on Thursday. I'll give you some more rules to help us narrow down that search for the zeros of our polynomial.